So my name is Carsten Rosseneffel. I'm co-founder and CTO of the European Advanced Networking Test Center, EANTC. We have been staging these kind of interoperability events here in Paris for the past few years, I would say. And it's with great pleasure that we are presenting the results of a very, very detailed test this year again. And so we have 12 vendors participating here. You can see the names on the left-hand side. We had more than 120 devices participating. We spent 3 weeks in our lab in Berlin, Germany, with more than 75 engineers from the participating vendors to get all of the testing completed. And in the end, we had more than 1,400 test results, if you can believe that, in 3 weeks. And all that is only possible through the excellent collaboration with people like yourselves. So without further ado, I will just hand over to Reza Rokui from Ciena, who will kick it off. And then Diego Achaval from Nokia will join the live demonstration. Stage is yours.
Thank you very much. Hello, everyone. The session today is about how SDN is going to work in a multi-vendor network. Just give you a short summary before going through the demo. As you are most likely familiar with EANTC, EANTC every year has the multi-vendor testing in the various areas. There are few areas. One of them is SDN and orchestration. There are other areas like MPLS, SRv6, EVPN, and timing. Today, the session that we do, the testing that we showed, go through the demo, is in the area of the SDN and orchestration. One of the test cases that we did, this is one of multiple tests that we went through that one for between various SDN controller and the node type. So one of them is latency-based. What we are trying to achieve with this one is we have a multi-vendor network. There are multiple nodes from various vendors. There is a SDN controller from Nokia NSP, which is going to basically go through the network. The intention of this demo is creation of the bidirectional TE tunnel where the constraint is latency. In this case, both constraint is latency, meaning that we are creating the LSP tunnels between two nodes. At the same time, with the metric for the objective also is latency. So both of them is latency based. And what we are trying to achieve here is when we are creating the NSP, the SDN controller, when it creates the LSP tunnel between two nodes, is going to monitor the IGP network. If something happened to the IGP network in terms of latency, in this case, is going to detect that because the intent of this LSP is latency, there is an intent violation, and based on that is going to trigger reroute of the LSP. We will go through that. Diego is going to show, but as a general rule, we are NSP as a SDN controller creates the LSPs with the intent to be the latency, is going to monitor it. When the health is violated, intent is violated, is going to reroute the network. The detail of the network is basically I have a network. Using the BGPLS, we are going to detect the IGP from the network. And from that aspect, we have a PCEP session between two PE nodes. One node is Ciena, one is H3C. And when NSP wants to create the LSP, is going to use the PCEP session. The type of LSP that we have here is segment routing TE. But the concept is so generic that you can apply it to SR policy, to RSVP. Doesn't really matter the type of the TE tunnel. But in this case, we did that one because this is one of the, as I mentioned, few test cases that we did. So Diego is going to go through the topology, explain exactly the topology we have, and is going to show the demo.
Hello, everyone. My name is Diego. Again, I work for Nokia, and we've been testing all of this Interop stuff related to path control and optimization for multiple years now. So we have the NSP here, and what you can see here is the test network that we use in Berlin. And as you can see, we have some red links, things that happened during the network. No, it's over there. Yeah. So we have a multi-vendor network. We have devices from H3C, Ciena, Nokia. So on our side, on the Nokia side, we have devices running SROS, devices running SRL, our new operating system. Not trying to do any marketing here, but it's worth mentioning, yeah? And so we have the topology. Let me just focus on a specific link here between these two nodes. And you will see that in the link from the direction from 201 to 208, you can see that we have a link delay of 10,000 microseconds, okay? So let's not forget about this, yeah? So now, I'll show you a couple of LSPs that we have here. So as you can see, we have Tunnel 13. This is going from H3C to Ciena, and CP123 is going from Ciena to H3C. And as you can see here, they are overlapped. They are very nicely optimized in there. So what I will do now is I'm going to select them, and I'm going to apply a series of configuration parameters to these guys. And I'm going to group them, okay, using what we call path profile. This is a proprietary thing, but there are extensions for PCEP to support this, but this still can be done in this multi-vendor environment. So we are going to give it an association group, or an association ID in this case. So we save that, and we are going to check in the map. So in the map, we will see that these LSPs are going to sit there. And let me show you here. So for example, the one in the direction from Ciena to H3C, we can see the segment list. So, but let me continue with the demo, right? Let me just show you one thing here, okay? So we have the LSPs, and as I was saying before, these two LSPs are using this link in the middle of the network, okay? And that link in the middle of the network got a delay of 1,000 microseconds, okay? So now if I go to my network, to my device, and I change that, so as you can see, I change the delay of the link from one value to the other. So I'm going to commit that value, yeah, that change. So now in the NSP GUI or the PCE GUI, this is just not just for the NSP PCE, but it also applies to any PCE like Ciena's PCE that can consume this information, okay? And you will see in a moment that the link delay for that specific link is going to increase here. Or maybe I will need to refresh the GUI, yeah? Oh, there you go. It changed, okay? It takes a moment, okay? So now ideally, if I would have been able to apply the path profile that I applied before, that I was trying to apply and it didn't go through, right? So for example, if I check this LSP here, right? And you see it doesn't have a path profile there, so it's not being optimized on delay. But for example, if I apply, let's say, a path profile on this guy, yeah. Let's see if I can apply this path profile to at least one of these LSPs. So you see it got applied, yeah. And if I now go again to the map, you can see that the LSP got optimized, okay. And a lot of things happened here. So we went, so the network had a problem in a link that increased latency in one direction, for example. And then of course, that information got propagated in the IGP, of course, in this case, ISIS, and all of that got propagated up to the PCE using BGP-LS, okay? Everything is standards-based, and as you can see, all of this information can be pushed from the network, from a multi-vendor network that has devices from every vendor to a third-party PCE, in this case being the Nokia NSP PCE. And then, of course, the PCE will consume that information, is tracking where those LSPs are placed, and if some of those LSPs have been affected by that link, the NSP PCE or any given PCE is going to optimize based on the change or based on how the actual delay is versus what's the constraint for that given LSP. Okay, if a threshold, for example, is not crossed, the LSP is not going to be optimized. But in this case, since we increase the latency value to a ridiculous value, right, we are forcing the threshold to be crossed, and for the NSP PCE, in this case, or for any given PCE, to fire an optimization task for any number of LSPs using that given link.
I might add one thing here. The application of this one is, for example, for 5G network slicing. When your intent for the slice is latency for URLLC, low latency, you can basically imagine that the tunnel which is created between two PEs, Ciena and H3C, is the low latency network slice that you created. And as Diego mentioned, the SDN controller intelligently listened to the network, grab the changes that happen to the network. For example, he changed the latency from 1,000 milliseconds to 15,000 and rerouted to accommodate the intent, which was the latency, because we wanted to have a latency below certain limit. And this is the way that you will see that the change in the traffic engineer tunnel happen in the background. And the whole idea of this demo is to show that the SDN controller in a multi-vendor environment can detect the network changes and change the intent as needed.
So, and just to finish, now that things have worked, as you have seen in there, so let me just change the delay static to the original value, right? So we click on the link again. So if you check here, so this is going to change to 1,000 in a moment. So just give me one more second until so you will see it will go back to 1,000. And of course, in this case, the PC will not going to react to this specific change. So we will have to launch a manual optimization task. So you see here, it changed. So what I will do now is I will optimize the LSP from Ciena to H3C, and you will see that the other LSP is going to be optimized too, right? Because they are grouped together and they have a bidirectionality constraint applied. And
the reason for this one is when the original LSP changes to the rerouted, the rerouted one still is okay. If IGP changes, there is no need to go and reroute the LSP because everything, the intent is not violated.
Correct.
But if he goes and change one of the link on the path of the LSP, is going to be rerouted. So it shows the exact content is related to intent based, not the Correct. Reaction to the change of the Correct. IGP network.
Exactly. And to that point, what I wanted to show you finally is here, for example, we have this configuration that we have applied to these LSPs. And as you can see here, we can define a max latency, which is the max latency that the LSP is going to, or the slice, for example, this can apply to a group of LSPs forming a slice. So this is the max latency per LSP, and this down here is a threshold that the PC is monitoring. And if that threshold is crossed, then the optimization task for that slice or LSP is going to be fired. Okay, and that's it from my side. Yeah. Thank you very much for being here today.